Hello everyone, my name is Larry Sharp and I am an application engineer here at Chroma System Solutions. Thank you all for joining us today. Today we're going to be covering stators, transformers, inductors testing for safety and quality. And we're also going to be talking about our 19036 combinational tester, which does a great job testing these kind of devices. Before we get started, I just wanted to let you know we will be muting all the microphones for everyone during the presentation, but we will keep the chat room open. So if you have any questions along the way, please feel free to send us a note in the chat room. We have people watching the chat room that will help with answering all of your questions. Also, before we get started, I'd like to give a thanks to one of our project managers and engineers that this is a lot of the information and a lot of the things I'm going to be sharing with you come directly from Mr. Kenny Nye, and he's done a great job supporting us with this equipment as well as educating us on the equipment too. So Kenny, thank you, and I appreciate all your help. So let's get started. Stators, transformers, inductors, testing for safety. When you think about it, if we just take one portion of what we call wire wound type components, a large part of that would be AC motors. And AC motors can be used in anything from fans and pumps and compressors, elevators, you name it. Even in household appliances, everything from your mixers and blenders to refrigerators and even your treadmill. Medical equipment uses a lot of motors for everything from positioning the beds, the operating tables, respirators, pumps, you name it. They have so many different applications for it. And of course, vehicles, electric vehicles especially, have a electric motor, but also internal combustion engine automobiles such as have things such as starter motors and injector coils and various types of starter coils. And our 19036 was specifically developed to help support all of these kind of devices. In addition to electric motors, it's also transformers and inductors. And as you can see, they come in such a variety of shapes and sizes. The manufacturing processes for these can be quite brutal. If you've ever seen how these devices are actually manufactured either by hand or with using automated devices, the windings can take a real beating during the process. So the wire used in each of the windings uses just a varnished enamel type of insulation. In between the layers, there may be other types of insulation. So all of these things, if damaged, can produce some major problems for any one of these devices. So electrical safety detection of defects and faults is mandatory. It's even defined in many different standards. So things that can happen during manufacturing defects, you can have everything from faulty material, the actual wire itself, its insulating material can have some kind of a fault in it. You can find material fault in the actual tape and the actual material used for insulation. There can be things like windings shorted phase to phase, internal windings shorted turn to turn, windings shorted to the chassis or ground or core, and various other types of breakdown due to some type of contamination within the windings, abrasion during manufacturing, physical damage, defects to the wire during storage, sharp edges on the core material, laminations and housing that can cut through the insulation. So testing is critical. So Chroma created the 19036 to do just that, to do multiple tests, because not one test by itself can do a complete job of determining a fault within those types of devices. So it includes things like AC withstand voltage, DC withstand voltage, or both of these are referred to as also high pot tests, insulation resistance testing, DC resistance measurements of the windings themselves, and impulse winding tests. So by combining all of these in one tester, it gives you one way to do a complete test on all of your devices, such as wire wound devices for transformers, motors, and inductors. So when you look at the unit, our group did a great job in developing a piece of equipment that has a large display, easily viewed for all the information during the test, as well as very easy to use for entering and setting the parameters for the programs for each of the tests to be developed on this product. You can use the keypad to do the numeric keypad for entering data. You can also use the function keys for directing and going through different steps within the program. It also, as you can see, has 10 individual channels. Each channel has a sense and a source. So between two channels you can get a 4-wire measurement, or between each channel with respect to the return you can do a 2-wire measurement. The unit has so many features on it that I'm not going to cover everything that I've got shown here on this screen, but I'll just highlight it. It's a goes up to 5,000 volts AC, up to 6,000 volts DC, 100 milliamps AC, 20 milliamps DC for high voltage withstand voltage testing and or high pot testing. Insulation resistance all the way up to 50 gigohms. DC resistance measurements down to the lowest ranges in 20 milliohm range, which gives you measurements reliably down below 1 milliohm. Impulse winding testing up to 6,000 volts does a great job doing 200 megahertz measurement sampling rate of the data points that make up the waveforms. We'll talk about that a little bit later in this presentation. We already mentioned the 10 channels for either 4-wire or 2-wire measurements. There's other things, contact checks we'll go through in a moment. And internally, as I mentioned before, you can do up to 200 programs with up to 60 steps in each program, stored internal memory in this unit. There's some other options that we're going to be talking about, software as well as adding LCR meter to the unit, and of course the various interfaces as well. So going on to the next level, I'd like to talk about AC withstand voltage and DC withstand voltage. That is a test that's been around for quite some time. It's referred to as a high pot test by most people. And with this test on a transformer or on the motor stator, you'll normally measure winding to winding, trying to determine that the insulation between the windings is intact and meets some specified requirements. You can also measure between the winding and the housing on an electric motor, or the or any type of mechanical housing, metal housing around the device. When you do this test, you normally apply the high voltage, you measure the current, and you look for excessive leakage current that's usually measured as an RMS value. But in addition to that, we've added the ability to also measure short various transients, peak current measurements that would indicate either a breakdown or arc or flashover. And so this is also a separate test that can be detected at a peak current, and we can set the parameters for that as well for pass-fail. Like I mentioned before, there's a lot of standards related to safety, and specifically for doing high pot testing of various devices. Two that come to mind are the ones used for motors, especially the UL1004 is for electric motors, and it also the GB14711. That's a standard that includes or requires a cutoff current up to 100 milliamps, and the 19036 AC withstand voltage handles that with no problem up to 100 milliamps. Insulation resistance is a similar test to the DC high-pot test, and it results in a measurement that is shown or displayed in ohms rather than in amps and volts. So the AC withstand test that we perform, we can program it manually on the front of the unit. We also, of course, have software available. But what I'm showing here is on the left is the actual display capture on the unit for setting up a program step for a AC high-pot test. And you can see that in addition to giving us the voltage and the high and low limit settings, we also can do the arc detection, but we have one other feature called real. This is real current versus reactive current, and we can also use that as a measurement and set a threshold for that as well. The test can be set for a ramp up, a dwell time for the test, or a test time, and a falling edge time. It also includes something called a high frequency contact check. This is unique for detecting the actual unit being attached to the device under test. So it ensures that the 19036 Chroma test equipment is physically testing or physically connected to your device under test. We'll go into a little more detail on that later. Down below you'll see internal scanner 1, scanner 2. This is where you select the various channels that you're using for this particular test. And I mentioned before that you can go with our 2 additional optional scanners all the way up to as many as 40 individual channels. On the right-hand side, you're going to see the actual display of the results of the test. I like it. It gives you a great big reading of voltage and current for the AC high-pot test, but it also gives you down below the actual parameter settings for the test itself, as well as gives you pass-fail data. The other thing that we do with this unit, because AC and DC high-pot testing alone and insulation resisting testing alone cannot detect all types of failures, especially failures within the winding itself. So the impulse winding test is included for that. If you're not familiar with impulse winding test, we apply a high voltage for a short duration right across the inductor, driving the winding, and while we do that and then remove it, we look for the waveform that is generated, the voltage waveform. And what we'll see, like the one you see here, is that you'll see the instantaneous voltage right at this point, which is a very quick rising edge, and it goes up to the peak voltage applied. After that, you'll see it decay, and while it decays, it'll start to see a ringing, and the ringing is caused by stray capacitance or possibly a cable capacitance with respect to being in parallel with the actual winding. So the inductance of the winding and any stray capacitance will be reflected in a resonant frequency and a ringing waveform like this. So then we take and look at the data points that make up this waveform, and from there we can do various analysis of the waveform and do judgments based on area, differential area. We do a Laplace calculation based on the entire waveform, and also flutter. And so by doing this, we can do a very good analysis of that winding to make sure it meets all the requirements, and there's no faults within the winding when we compare it to a known good unit. So this is just a quick reference of what area and Laplace detection we'll be looking at. So when you look at the waveform, the area under the waveform is actually detected and measured to determine if that area changes from a known good unit to the next to the device under test. And by comparing the area under the curve, we can determine that the unit does not have any type of breakdown between turns or breakdown between layers that would result in a change in the area. When we do the Laplace test, what we're looking for is a very fast transient change in the waveform that would be caused by something like an arc or flashover or partial discharge. But of course, it can also detect a complete breakdown in the winding itself between layers or between turns. So this is another great test that we perform to give you that added insurance that unit that you're testing is going to be good, and it's going to pass, and it will work well when it gets to the field. So just a couple more examples of this. So a normal good waveform that you see here in red compared to a device under test that has a failure, such as a shorted turn, would give you a sudden change in the waveform, but you can also see it also changes the area of the waveform during the ringing portion. So you'd be able to look at a large portion of the waveform and do this type of area comparison to give you good results to determining that your device under test is either passing or failing. And then again, as we mentioned earlier, the impulse winding test doing the Laplace test looks for faster transients such as partial discharge and arc and flashover, and that would occur with a very fast transient, a very short interruption of the waveform that would indicate one of these types of failures. And we can do that measurement by using what's referred to as a second order differentiation, and also doing a very high sampling rate up to 200 megahertz of all the data points that make up the waveforms. This is a screenshot of what the program screen would look like. This is an actual capture of a program screen on the 19036. So we give you a voltage, something called width. Width would be the width of the waveform used in this detection, as well as to determine the limit settings when compared to a sample. Pulse is the number of pulses. We can actually do multiple pulses for impulse winding test, or we can do most common is to do one. We can even do a pulse that has no judgment prior to doing the pulse that we would do for a judgment test. Down here you can see we can set the beginning and end on each of the different types of tests we perform. And the beginning and end is what you see here in the with the cursors. It determines what portion of the waveform we're going to use when we're testing that particular device. So we can also change that, like I mentioned, for each one of these four different types of measurements and judgments. Again, down here shows the scanner, the channels on the internal on the 19036, as well as two additional scanners, and you can select between any of these different channels to use for your test points for your device under test. When you look at the unit, the nice thing about it is the sample that you see here in red for your known good sample will be stored, and all subsequent tests after that for any like device would be compared against this. So when you do this, we normally do a sampling of a batch of units and determine what is a known good unit to use as our sample. But if you need information, more detail on this, please let us know. We'd be happy to go into a lot more detail about impulse winding testing. The results of this test can be displayed three different ways. The top one here on the left is what we refer to as the list. It lists each individual test or step test within a program, and it will give you each individual test pass or fail indication here, as you see. You can also get more detailed information by doing the test screenshot for each individual test. Here it shows you an impulse winding test, shows you the measured voltage, shows you the results of the 4 different types of test judgments, and also gives you the actual parameters for the test below, and then of course we'll give you a pass-fail indication. The one I like, of course, is this waveform that we can also display the waveform as the test results. The red waveform is going to be the actual unit under test, where the white waveform is the known good sample that it's being compared to. Down here you'll see it gives you area, differential area, flutter, and the Laplace test results, and will be used for judgment. If it comes up all green, you know you're good. Any one of those come up in a red, you know that it's failed. I'll show you an example here of a failed unit. This fails by area. The area test that we did for this one, the actual judgment was done at, I believe, 15%. You can see here that it failed by going up to 17%. The red, again, is the device under test waveform. The white would be the sample waveform. So you can see the various differences in the area and the shape of the waveform, and that's used, like we said, to detect if there was some type of a breakdown or difference in the 2 windings. Slide is that we also include a thermocouple temperature probe option for this unit, which allows you to, in low resistance measurements, include temperature compensation to get the best accurate measurement for your resistance of your winding. Another test that we do for DC resistance measurement is referred to as delta and Y measurements. When you're looking at a 3-phase device, a 3-phase motor or 3-phase transformer, often the windings may be terminated or configured either in a Y configuration or a delta configuration. And as you can see in the resistors and the drawings showing below, that is an indication of how those windings might be terminated. In a Y configuration, all 3 windings have a common termination that may be used as a neutral, or if it's not used and it's only a 3-wire measurement of those 3 windings, normally you would get 2 winding resistances combined when you make that measurement. Chroma's put together an algorithm internal to our firmware on this unit that allows it to detect or to differentiate and calculate the actual resistance of the winding of each individual winding. We also have that same ability to do it for a delta configuration like you see on the left. And with that, you would see that the windings wouldn't be in series, but they would actually be 2 windings in series, but that are actually paralleled across the winding under test, and that would definitely cause a lower resistance reading. So again, we can do a calculated value of the actual resistance of each individual winding to give you a proper measurement of that winding. When we look at it on the unit itself, on top here I've got a standard DC measurement without doing any type of calculation regarding a delta or a Y type measurement. Here you can see the winding I measured, which is the same winding as RAB on the 3 phases, measured 461 milliohms or 0.461 ohms. And you'll notice here that when I measured it using our delta connection, our delta calculation, it came out to be 692 milliohms, which is the proper resistance of that winding. In addition to doing the winding measurements more accurately and giving you the proper reading for that, we also include what's called a balance. The balance is a way to measure and compare each of the windings, each one against the others, to determine if they are balanced. If you're familiar with electric motors, balanced windings are critical to a good performance on an electric motor. It also, an imbalance could cause things such as an overheating of the winding and could definitely cause insulation breakdown at some point in the field. So balance is another test that's critical, especially for things like electric motors. Another test that we do that is an option is we can also include an LCR meter, one of our LCR meters with the actual 19036. We have connections on the back of the 19036 that bring the measurement capability from the LCR meter all the way out to each individual channel on the connections here that you see on our 19036 safety tester. So when we do that, we can now measure the actual inductance of each winding, but we can also do, in addition to each winding, we can do a comparison to measure the balance. Again, balance critical to stators and electric motors. And by doing this, we can not only we can measure the inductance of each winding and then compare it and use a limit for each of those as well to make sure they're closely balanced with each other. Another test that can be performed with this is the quality factor. We can also measure quality factor with the LCR meter attached. This probably should have been at the beginning of the presentation. This is what we refer to as a contact check, and we refer to it as a high frequency contact check. What it does is it actually performs a high frequency, approximately 1 megahertz at a low voltage measurement across the device that's under test, where you would be using it for a high pot test where you're not physically connected to a conductor, but each winding that has an insulation between it. And when you have two windings with an insulation between them, they have stray capacitance. So what we're doing is we're looking for that stray capacitance to determine that we physically are connected to the proper unit to be tested. In addition to that, we can detect if there's an open or a short prior to starting the test. So it's a great way to knowing that you are physically connected before you run the test and that you're connected to the unit properly. Now this only works for when you're doing an AC high pot test or for testing insulation resistance or DC high pot test. But when we're doing a test for the winding itself, such as impulse winding testing and DC resistance measurement, we can use something called a high-speed contact check. And these are included with each of those types of tests that I defined. And this will actually also indicate that you're physically connected to the winding that you're going to be testing, and that the unit, the device under test is properly tested. Another thing that we offer is software in order to do a complete test for you and to make the testing more easily set up. We offer a nice software package. It's referred to as a soft panel, and the soft panel for this unit is developed in LabVIEW, and it's a fully executable standalone software package. You don't have to own LabVIEW to operate it. So this particular soft panel can give you the ability to do all the programming of each of those steps as we defined them in each of the previous slides. But it can also capture all the test data and send it to a report and to a database where you can do statistical analysis for your manufacturing processes, as well as you can capture a report for your customer on the device under test. So it's a great piece of software, easy to use, and in addition to being able to create the program, store your programs, and edit your programs, of course it gives you that great ability to store all your test data. Also, other little sidelight into this is that you can also use like a barcode reader to, if your devices have some type of barcoding and labeling, you can then use that to make sure that you have the proper test program prior to running the test for your device, and also to capture the device's serial number or indicate the model number of the unit during test. The actual data that is recorded will be displayed in the software like you see it here. And this gives you, here you can see we ran 10 individual steps within this single program. And with those 10 steps, we were able to measure DC resistance as well as a DC resistance balance and average test. We also did the AC high pot test and an impulse winding test on all three windings, as well as a impulse winding test comparison. So we were able to do all those tests quickly, efficiently, record all the data, and give you an indication of pass and fail, all done within this software with our 19036. So this is probably not all the information that I should have presented to you, but within this amount of time, this was probably a good overview of everything we can do with this equipment. But if you want to know more about it, please reach out to me or to one of our regional sales managers. You can contact us through our website, or you can contact us through a phone and email to ask any question you might have. We'd also be happy to do a demonstration online of this equipment for you, show you how it operates, and if necessary, we could even do a test on one of your devices to show you what it would look like when we perform the test for you. So keep online with me a little longer. If you have any questions, please feel free to ask. We'll be happy to get to your questions. So I'm going to go ahead and stay online a little longer, and we'll open it up to a question and answer to your questions. So thank you, and please let us hear from you.